to be.
Yep.
There is a talk after me.
Yeah,
Okay, okay. All right, okay, cool. Yeah, hi everyone. I think I know some of you here. Okay, so who is taking 206 this semester? Oh, hello. I'm teaching 206 this semester. So yeah, welcome. Great pleasure to be here. Thank you for inviting me. I didn't even know about this event before they invited me. So very cool. Also, how many here are not from the US? Oh, okay. So there are some external audience as well. But yeah, so it looks like most of the people here from the students from here. So I'm my name is Jialin. So I'm an assistant professor here at SOC. So I joined SOC about 4 years ago during COVID time. And then I do systems research, so both operating systems and distributed systems. And coincidentally, I also teach operating systems and distributed systems. So today I'm going to talk about a particular topic that I was part of, and then I'm also continuing working on this research direction, which is operating systems design for fast I/O. Alright, okay, so I would assume everybody here knows what I/O is, and I would assume everybody have interacted with I/O in one way or another. Turns out I think most of you are interacting with I/O right now with your laptops and phones and tablets. Maybe you don't even know you are doing I/O. Right? Every time you have type a URL in your browser, you are interacting with I/O because your browser is sending packets to, for example, Google to fetch some data, right? So that's I/O. Every time you are writing something on your notepad, your Microsoft Word, it auto saves, and when that saves, it's writing to local disk, right? So all these are I/O. So you're probably very familiar. So the traditional view of I/O is that you have a processor, right? So the processor view of I/O is some peripherals. Right, so you have this I/O interface between your CPU and your I/O devices, being a disk so that's a network interface card. So today the I/O I'm mostly focusing on storage and networking. So fun fact, I think I was teaching 206 last iteration. There were people asking me what is a spinning disk. I was like, okay, the students these days are very young. They don't even know what's a disk, spinning disk. But yeah, when I was first introduced to computers, we only have access to the SSD was not a thing, right? So it was only spinning disks. So the point is that back in the day, when I was younger, so I/O is supposed to be these very slow devices. Can you imagine, so I took some of these numbers based on historical fact in the 90s. So you have your spinning disks of a speed at around tens of megabytes per second transfer time. And then each time you access some data on your disk takes 10 plus multiple tens of milliseconds. So you probably don't have an idea of what that number means, but it's very slow. Okay? Yeah, I think I was downloading something the other day, and I found that I was actually downloading faster than that. So back in the days, it's very slow. And then for network interface card, there's before 2000, it's very common to have hundreds of megabits per second up to a gigabit per second. The gigabit per second Ethernet has been around for a very long time. And when I was first introduced to computers, I was using the modem. I don't know how many of you here actually use a modem before. They are extremely slow.
Yeah,
right? So
plug into the laptop like this part on the side.
Yes. And then there are. So I don't know which year you use those. I mean the time I use is 56K modem, which means the transfer rate is about 56K bits per second. But not even much slower than those. But anyway, so the high-level takeaway point here is that back in the day, CPUs are considered very, very fast. right? But the I/Os are very, very slow. So when you design your system, you take that as an assumption. Right? Your assumption is that I/O is extremely slow. Most of the time, your CPU is waiting for I/O to complete. Right? So that's in the 90s. Okay, fast forward to today. It turns out I/O technology has been improving, actually dramatically. So these are some more modern I/O devices. So on the left is a NVIDIA Connect X7 NIC, which is I think this is the latest card from NVIDIA. So it supports up to 400 gigabit per second Ethernet, which is extremely fast. On the right, you have an Intel Optane DC SSD. It's an NVMe SSD. It doesn't look like a disk, but it is a disk. And it supports more than 7 gigabytes per second transfer rate and 1.5 million I/O per second. Right? So, yeah, this is a lot faster than what I just showed the previous slide. And that's not just these devices are fast. I mean, we're looking at historical trends that I/O devices are even getting faster in the future. Right? So here I show both the Ethernet projected Ethernet speed for the next few years. Right? So we get up to a few terabits per second. So that's a humongous amount of data you're transferring. And then on the bottom right, I show you the roadmap for another networking technology called InfiniBand, which similarly show multiple terabits per second transfer rate. Right? So, takeaway of this slide, I/O devices are getting extremely fast. And they will be getting faster. At the same time, for those who are reading computer magazines and news, probably heard the term like Moore's law is dead and things like that. Or I think we also teach that at the US. Right, so this is a known fact. It turns out Moore's law is not dead yet, so that's a misconception. So thanks to NVIDIA, we are still pushing the kind of the chip density or the number of transistors on your, for example, favorite GPU, right? So they're still getting more. But there's one thing that actually stopped. Do anyone know what law actually stopped? Okay, I need to ask your architecture lecturers. So one thing, there's a thing called dinar scaling. Anybody here heard dinar scaling before? No, we'll go take an architecture class. So dinar scaling essentially says how much more frequency you can add to your processors. So when I first used when I got my first computer, I remember it was about 200 megahertz. That's the CPU frequency. So that's in the early 90s. And then it just keeps increasing. Right? So every generation of CPU core, your frequency increased. Right? So up to the point about early 2000s, when it gets to about 1 to 2 gigahertz, your CPU frequency. And then, so this diagram essentially shows the CPU frequency versus time. At some point, it stopped. Right? So you can go back and check your laptop, your desktop, and see what is the frequency of your CPU cores. It's more than likely that's between 2 to 3 gigahertz, which is the same as, 10 plus years ago. Right? So the CPU frequency has not been increasing. Well, that's due to different physics laws, and then there's cooling issues. You cannot cool your CPUs if it gets even faster, right? So the result being that CPU, you can still get more cores or more your GPU cores, right? But each one is not getting any faster. Okay, so you at most get 3 gigahertz. All right, okay. So these are some hardware trends. How does that relate to operating systems? Right? So traditionally, the operating system kernel actually handles all I/Os. Okay, so if you have taken an operating systems class, I hope this is something that you already know. Right? So the operating system is responsible for handling all I/O operations. So here I show, you don't need to fully understand what the diagram says. This is the storage I/O stack. So on the top you have your applications. You write these applications that issue things like read and write system calls. As a user, you mostly forget. You mostly just ignore what happens below that, right? So just do read and write. And then at the bottom layer, there is your storage block devices, your hard disks, your SSDs, right? But there are so many things happening in the middle, right? So how does your read and write system call translate to your bits on your block device? That's all managed by the operating system, right? So the operating system implements the file system, implements a block device interface, right? And then at the bottom layer, it has the driver interface as well, right? So a lot of complexities here. So the same applies to networking I/O, right? So networking I/O, so if you have written any network programs, you know that you open sockets, right? And then you send, receive packets, right? So that's the application level interface, what we call the POSIX interface. And then at the bottom layer, you have your network interface cards that just bump bits into your Ethernet wire. Everything, there's a lot of complexity in the middle as well, right? So when you get your data from your application, how do you move that application buffer data to your NIC device? So that's all handled traditionally by the operating system kernel. Okay. So what's the issue with OS kernel processing everything here? First problem, okay, this is not intended for you to read. Okay, so I just want to show you that the operating system, or should I say, this is for Linux, right? So the Linux I/O stack is extremely complex. So this is, I think, a architecture or a call graph for networking stack in Linux a few years ago, at least. So I think I used to refer to this diagram when I was trying to debug some networking issues throughout the kernel. So a lot of pain. So many things happening there. They're extremely complex. Why do they need to be extremely complex? First, this is not an easy job, right? So doing I/O, right? But more importantly, Linux is running on millions of devices these days. Right? So a lot of the devices these days use Linux. Now Linux needs to support a lot of different scenarios. So there's so many users, so many different workloads, right? Even your Android phones use some form of Linux, right? So, it just needs to handle so many cases. But because it needs to handle so many cases, it has to be complex. There is no other way around. Okay, so what's the problem with OS I/O stack being extremely complex? If you taken the operating systems class, you know that the operating system kernel runs also on the CPU. So that means the CPU now needs to handle all these complex tasks for processing I/O in the kernel. Okay, so to give you some sense of why that is a problem, so this work we did a few years ago. Actually, about 10 years ago, actually. So we benchmarked a particular application called Redis. You don't need to know what Redis is, but simply speaking, it is a fast key value store. Essentially, you want to store some data into, this is like a very simple database. And so we are testing, and Redis is also you can use Redis as a server, right? So you can actually send requests to store something to Redis, and then, you send a packet to Redis, the Redis will process that packet, do the actual store that data on storage, right? So here we are actually benchmarking the performance on the Redis server, right? So when they receive client requests to store some key value, and then eventually write to some disk. Okay, and then we try to benchmark, try to understand how much time is taken to process each of these Redis requests, and then attribute them to the hardware, the operating system kernel, and to the application level. Okay, so there are two types of requests. There is the GET which is I want to read something from Redis key value store, or there's a set which I want to store something to the Redis key value store. Okay, and then in both cases, we figure out, the kernel is actually taking most of the time handling these I/O requests. Right? So that means for each request, you're spending almost all your time just inside the OS kernel through your I/O stack. Okay, and then here at the bottom, I gave you some raw performance of these I/O devices. On the left is the network interface card. So back then it was a 10 gigabit network interface card. So if you do the back of the envelope calculation, you see that for 10 gigabit network interface card, in theory you can get 1 kilobyte packet every 2 microseconds. And then if you look at the overall processing time running Redis, each GET request is taking 9 microseconds. What does that mean? That means it is actually not keeping up with the hardware itself. If the hardware is sending packet at the maximum rate, we cannot even handle all of them. And because you are supposed to handle everything within 2 microseconds. Right? So now you can see that the network hardware is getting so fast that your kernel processing out there is too slow. Yeah, just keep up with it. Okay, so that's a few years ago, right? So these days, in my cluster here at AUS, we use 100 gigabit per second NIC. Right? So all our network interface card in my own cluster have 100 gigabit per second. And if you do the calculation, that means every packet that if you receive at the maximum rate, you receive a packet every 200 nanoseconds. Right? So if you want to handle this kind of I/O, your I/O stack needs to be able to process packet in every 200 nanoseconds. Clearly, this is not enough, our current design. Okay, so here I just break down a bit more on what's happening in the kernel I/O, right? Which part of the kernel I/O is spending how much time. The details here don't really matter, right? So just give you a sense that there are a lot of stuff you need to do in the kernel, right? So there's a lot of complexity as explained, and then there's also a problem with context switching, right? So which I didn't write it here, but it's definitely another big source of overhead doing I/O. Right? Context switching means that because you need to issue this I/O from application which runs in user space, and then your I/O stack is in the kernel space, every time you need to do a switch from user space to kernel space, which takes quite a bit of time. Right? So adding up, right? So eventually you have a very high overhead, right? So just looking at the I/O overhead on the read path, your total, the median value is about 8.67 microsecond. And your tail latency, 99 percentile tail, can go up to 15 microseconds. So very expensive. And on the right side, writing to disk is even slower. All right, so we talk about the problem. Hopefully I convince you that it is a problem. Right? Okay, so you probably haven't met this problem on your laptops yet because your laptop's I/O is not fast enough yet, but maybe in the future. Right? So we all face this problem. But at least in data centers, this has been a problem for the past 10 years. All right, so we have a problem. Do we have solutions? Of course, yes. Right? So people are smart, and then they are figuring out solutions to solve this problem, and starting from data center. Right? So data center people figure out, okay, our I/O is too slow, right? And then it cannot support all our needs. So what do? So people come up with a different way of doing I/O, right? So the problem we face is that the kernel is very, very slow. If the kernel is very slow, what do? We bypass the kernel. We just get around the kernel for every I/O request, right? So this is called kernel bypassed I/O. So there's this famous framework called DPTK. So I don't know if anybody here heard about DPTK. So using DPTK framework, what you can do is that you can have your network I/O directly routed to your application without the kernel touching anything. Right? Of course, there's some complexity here, right? So it doesn't come for free. For example, the DPTK framework needs to provide this called pull mode drivers that enables the application to actually directly pull these network interfaces to get the packets. Right? So for networking I/O, you have DPTK, and for storage, you have something similar called SPDK. Right? So which similarly, right? So you can have these pull mode drivers in user space for accessing storage devices directly. So they just completely bypass this the kernel when they do I/O. So one issue with this is that if you completely bypass the kernel, that means you are talking directly to a hardware device. But the hardware device is not a nicely friendly interface, right? So you are very used to, for example, using a file system, right? So you typically, okay, if you open a file, you write to a file, right? You close the file, stuff like that, right? So it's very easy. When you work with block devices or storage devices, they give you individual blocks, right? So I have a disk block of 512 kilobytes. You go ahead and figure out how do you store files in these like a billion blocks, right? So the kernel actually help you with managing all of these complexities by providing a very nice file system API or abstraction. But with SPDK, DPTK, that is all gone, right? So application just directly access like these storage blocks or network I/O like small packets, right? So you no longer have your send receive, TCP/IP calls, right? So that's not great, right? So the first step people propose on top of DPTK and SPDK is what we call a user level I/O library, right? So by using this DPTK or SPDK, then you can write a library that actually provides the same interface as your traditional Linux POSIX interface. Right, so on the right, I show you one research work that probably pioneered this line of research. It's called MTCP. MTCP is a user space library. So you can imagine this is any other library like you load in your program, but inside this library, it actually implements the entire POSIX API. So the application using this library can still use the traditional accept, wait, like your send receive calls, but internally it has a different TCP and IP implementation, right? But the nice thing is that using this application level library, right, so you can have the same interface, but also you remove all the kernel overheads because all the packets directly just go to this user space library without any kernel processing. And then you just do a little bit of processing in this library, and then you get your TCP/IP stack. Okay, so that's very fast using this user space I/O library. What is the issue? Okay, well, typically when doing my lectures, I will probably have a quiz here, but since this is not a lecture, I will just give you the answer. What are the issues? So the issues are, you need to remember what are the purpose of running an operating system. So why do you need the operating system in the first place? Okay, so the abstraction and interface is only one of the reasons, right? So it gives applications very good interfaces, but the operating system is also doing a lot of other things, right? So I list a few of these things here, right? If your applications have direct control or access to I/O hardware, then who is responsible for doing things like protection, isolation, resource management, fair access, security, and all the other kind of jobs. Right? So traditionally, these are all done by the operating system. Okay? So you may ask, why do we need this? Okay? Right? So in particular, why do we need this for I/O? Right? So if you don't have any of this, right? So one application can just hog your I/O device, for example. Right? So you can have a malicious application that just like completely take over the entire I/O device, and then your applications cannot even use any I/O, right? That's one problem, right? And then potentially the malicious application can use this direct I/O access to spoof your data, right? So your traffic, they can just see your data, right? Your sensitive data. That's even worse, right? So we still need someone to help us maintain the security, the privacy, isolation, fairness of all these applications sharing the same machine. Okay, so as I said, these are all traditional operating system responsibilities. Alright, so the research question we were asking back then was that can we have high performance I/O without compromising OS protection? Which means can we have both high performance and high security? Right? So we look at one interesting technology. Right? So this is roughly during the time where cloud becomes very popular. Right? And for you to have a cloud, there's one particular technology that's important. It's called virtualization. Right? So because you have multiple of these tenants, users all share the same cloud machine, right? And then you need some way to provide them a virtual machine interface so that they think they are operating on a physical machine, but in reality they are sharing with other people, and they need to make sure the security and everything, right? So I hope everybody here roughly understands what virtualization means. But there is a particular technology that was very recent back then, was called hardware I/O virtualization. So what is hardware I/O virtualization? So imagine you have a cloud machine, and then you have a bunch of these tenants all running on the same machine. So you spawn this virtual machine or kind of VM guest, one for each tenant. Okay? So that's fine, but all these guest virtual machines are accessing the same physical I/O hardware. For example, they are sharing a disk or sharing a network interface card. How do you make sure that each one has a proper access to this? Each virtual machine is having a proper access to this I/O device. Yes?
I think I might have seen this before, like the Arch wiki or something.
With what?
There was some wiki about something about libvirt and KV.
Okay, yeah, that's all related. Okay, yeah, that's a good point.
I had to set up like some sort of a virtual device with its own UID, connected to the.
Yes. There are a few ways for virtual machines to access your I/O hardware, right? So the most traditional way is that they all leverage this called hypervisor. So hypervisor is this system software that manages all the virtual machines, right? So the default option is that you have your hypervisor to also help you manage the I/O devices. Okay, so that is definitely okay. What's the problem with using hypervisors? It is very slow. Similar to OS, hypervisors also run on CPUs. So that means every VM's I/O access will need to go to the hypervisor for the hypervisor to manage these I/O requests, right? So what's the other option? Or there is also another option is called PCIe pass-through. You can pass through your PCIe device directly to one VM, but what's the problem? Then your VM has all control over that I/O device. The other VMs cannot access it. So pass-through can only work if you have only one VM. Right? So what if we need to have multiple VMs, and then we also want to remove the hypervisor overhead? So that's when hardware I/O virtualization comes into the picture. So essentially, what hardware I/O virtualization does is that each I/O device is then represented as what they call a physical function. Right? So your storage is a physical function, your network interface card is a physical function. But with I/O virtualization, it can represent each physical function as multiple virtual functions, or these VMs. So each virtual function you can imagine is like a virtual storage device of this big physical storage device, and then each virtual function will have its own registers and own. So all these are dedicated hardware for each virtual function. Right? And then what you do is that you actually assign each virtual function to each VM. Right? And by doing that, then each VM will have direct access to a virtual function, which you can imagine is let's say it's just a child of your physical function. Right? But it doesn't need to go through the hypervisor, right? So it's all direct hardware access. Okay, so this is a particular technology. It's actually called single-rooted I/O virtualization, or SRIOV. Okay, with hardware I/O virtualization, right, so there are a few benefits. Right, first, you can enable multiplexing. Right, so each virtual PCI device or virtual function has its own registers, queues, interrupts, which are like so that means you don't need to virtualize these anymore. Okay, and then you also have protection. So with help with things like IOMMU. I think that makes sure that your application using a virtual function is not going to write to some other VM's virtual function, right? So there is like this protection unit in hardware that ensure that your I/O you're not touching other people's memory and I/O, right? And also there are things this called packet filters, right? So we can do some filtering and then redirecting of traffic to each responsible virtual functions. Okay, and lastly, you can also do some hardware level I/O scheduling. You can do rate limiting on each virtual NIC or virtual function, and do some packet scheduling, etc. All right, so the details here are not important, but you just need to understand this is a pretty cool technology that enable each VM to have their own access to a virtual hardware interface. Okay, so this is just for virtual machines. So what does that have to do with our topic today, which is operating systems and fast IOs? Okay, so the first thing I did is that I just put all the traditional kernel's responsibilities in this middle box. Right? So it's responsible for things like running API, naming, access control, protection, etc., etc. Right? So what we are going to do next is that we are going to reassign some of these responsibilities or move them out of the kernel. Right? And then let's see how do we reassign some of these responsibilities. First of all, remember, once we have I/O virtualization or hardware I/O virtualization, we can already move things like protection, multiplexing, and I/O scheduling down to the I/O devices because these are already provided by the SRIOV or hardware virtualization hardware, right? So these can be done completely in hardware. And then all of the remaining things, we can put the API and I/O processing into application. So this is similar to the MTCP idea I told you, right? So this is I'm doing I/O processing as a user space library. So I can still do that. So I move that into the application. And then all of the remaining responsibilities in the kernel, so I can do a few things, optimizations to remove the copying. So I'm not going to detail how we do that, but so the only thing left is like naming, access control, and resource limit. Okay, so that means we still need to do something in the kernel. Right? So we cannot completely get rid of the kernel. So what do we do? So here comes the key design idea of our research. So the key idea is what we call the separation of the control plane and the data plane. That means we divide the I/O processing into two kind of planes. One is called the control plane, and then one is called the data plane. Okay, so to be honest, this is not the terminology we designed. The control plane and data plane separation is a very common design pattern in networking. So if you look at network switches, any of your network devices, they all have this control plane data plane separation. Right? So usually when you have a network switch, there is the data plane, which is like forwarding packets in very fast. And then you also have a control plane who is the network admin who goes in there and type, route this packet, route this IP packet from this IP address to that port. Route that packet IP address to the other port, or block this packets from these IP addresses. Right? So that's the control plane, which is the administrator inputting rules into the data plane. So we apply a similar idea, right? So we separate OS I/O stack into a control plane and data plane. And then we say that the data plane should be very, very fast. Right? So you have your I/O devices, right, doing the SR-IOV things, and then it goes directly to the application, which has the user level I/O processing. But we also want to have the kernel to have some way to control these things. So we have all the control plane done in the kernel, but the key here is that the control plane is not invoked on every I/O operation. So the control plane is invoked very rarely. So turns out we only need to do this in the beginning when we set up the I/O queues and stuff. Okay, so that's our research work. Just give a bit more details. Things like what does the Aracus control plane? So by the way, the research name is called Aracus. I don't know how many of you know what is Aracus.
And from Dune.
From Dune, yes. Turns out the one of the authors are a fan of the Dune series, but that's not related to the research. So the control plane is responsible for things like access control, right? So who can access what, right? But that we only need to do it once, right? When we configure the data plane. After we've done this once, then the control plane is not, the access control part is not involved anymore. And then we can do things like resource limits, right? So we can limit, for example, this application can only receive 1 megabytes of data per second. Then we can also do this from the control plane, but usually we don't need to do that for every I/O request. And there are things like global naming, but in the interest of time, I'm just going to skip some of these details. And of course, for the data plane, as I said, you just do user level I/O processing, your TCP/IP stack, and then you provide POSIX compliant interfaces and stuff like that, right? So that's the overall design. Okay, well, I do have some performance numbers, but I don't want to spend too much time here. This is not a conference talk, and you just need to know that it is fast. Okay, it is very, very fast, and then it's even faster these days. These are already old numbers, but I will not bore you with all these different numbers here, but it's fast. Okay, but I want to just, in the last 5 minutes, just talk about some other interesting stuff here, right? So before I wrap up. So hardware I/O virtualization is not the only way to enable secure fast I/O. So in the years following our research, there are also other research directions that explore other techniques to enable fast I/O, but without compromising security. So the first approach is what we call microkernel style I/O services. How many of you here know what microkernel is? Okay, a few of you, right? I'm disappointed that my students from 2006 did not raise their hand. I taught you guys microkernels. Okay, so maybe a 20-second premier lecture on microkernel, right? So your traditional kernel, Linux, is what we call a monolithic kernel. A monolithic kernel is you have all your code, your kernel code running in kernel space, right? So there's a big chunk of program running in your kernel space, right? Microkernel is different. Microkernel says that your kernel should be as small as possible. So you have a tiny little piece of code that just manages the most important thing about an operating system, right? And you run all your other operating system services, things like file systems, things like device drivers. These things do not run in the kernel space anymore. So these things run in user space as different processes, right? And then whenever you want to, for example, to access file system, then you just send what we call the inter-process communication, or IPC. You can imagine, I just send a message to this file system service in user space to do this, right? So short up, just in summary, kernel is tiny, all your services are processes running in user space. How does that apply to I/O? Right? So instead of having your I/O stack in kernel, as in monolithic kernel, so you have then you move your I/O processing to a user space process, right? And then you have, so that's so that user space process will have direct access to your hardware devices using things like DPTK. Right? So you run DPTK in this user space process, and then your network module will have direct access to your NIC. Okay, so you may ask, wait, if you use DPTK, so isn't that have security problems? Right? So no, right? The reason is that this user space process called a microkernel network module is not an application. So this is still the part of the operating system. Right? So this is managed by the operating system, and then the application cannot touch this microkernel network module. Can someone tell me why the application cannot touch this module?
Process isolations.
Yes, right. Because it runs in a different process than all the other applications. That is based on process isolation or address space isolation. It is completely protected from the applications. Okay, but here you do have a little bit more overhead here because the application, when they want to use I/O, they need to issue an IPC to the user space. The network module. But they optimize it pretty well, right? So the IPC is very fast. So this is based on a research from Google. So actually Google runs this, what they call SNAP network architecture in their Google Cloud or Google data center. Right? So they use this kind of architecture within Google. So the last approach I'm going to cover today is called NIC hardware offloading. Right? So this is, I think, is pretty cool, and I think this is very recent. So in the last few years, so suddenly there is this trend of putting more processing power on your network interface cards. So that means your network interface cards are no longer just the dumb device you had before, that's just pumping packets. So this one is called NVIDIA Bluefield 3. So some marketing genius came up with this name called data processing unit or DPU. Yeah, that's just marketing terminology. But it's a network interface card with some CPUs on top. Okay. Well, there's some. This is essentially a very complex SoC system on chip with your traditional network hardware units, but also with so these are the ARM CPUs, right? So you have, I hope those guys can see it as well. So you have your ARM CPUs run on the NIC hardware itself. And then you have things like some ASIC accelerators on this SoC as well. So that means your NIC hardware is now a computer that can process things. And sometimes it can even process things faster than your CPU. Okay, with this kind of NIC hardware, what can you do? So you can start, when I say offloading, I mean you can run some of your traditional OS services now in the NIC hardware itself, because now it has all this processing power. So it suddenly opens up a lot of opportunities. So this is one particular interesting case that is actually deployed in Microsoft data centers. So Microsoft data center these days, or they call the Microsoft cloud is called Azure. So Azure networking actually runs a particular service traditionally run in operating system now in this network interface card. They call smart NICs, right? There are NICs that are smart. So what they run is called this virtual switches. I don't have time to explain what virtual switches are, or if you heard the terminology OVS. So traditionally, this OVS runs in software in the operating system kernel to help manage network virtualization. But now they move all that network virtualization infrastructure to the smart NICs. So that's another way to keep up with the very fast I/O. Okay, I think perfect timing. So in conclusion, so if you hopefully after today's talk, you at least know that I/O devices are getting faster, and then if you do all the I/O processing in kernel, it's way too slow, and then the kernel becomes the bottleneck. And then I introduced a few approaches to remove this kernel I/O overhead, right? Starting with our research on hardware I/O virtualization, and using that to do a separation of control plane and data plane, which we build a Aracus operating system, and then some more recent approaches using microkernel-based I/O services and smart NIC offloading. And with that, thank you everyone, and I'm happy to take questions. Yes, go ahead.
So what do you think of I/O ring as a way to provide faster I/O?
Okay, that's a good point. So I/O ring is some more recent, like Linux-based approach to. I think this is certainly one step forward. So it gets it improves the traditional I/O performance on your traditional Linux, right? Without you to need to like use any of these fancy features. So I think it's good, but that also means you probably need to modify your application to be able to use it, because you need to use the I/O ring interface. So for legacy applications that you don't want to change, that's a bit hard, but I think there's certainly one improvement. Right? But thanks for the question. On that note, I also remember there is also this other branch of technology that tries to improve I/O performance called eBPF. I don't know if people heard about eBPF. And then there's a related technology called XDP, or the Express Data Path. These are all recent kernel advancements that try to improve the I/O performance by bypassing some part of the kernel, and then lets users write programs to run in the kernel space to have very fast I/O. Okay, any other questions? Yes.
You mentioned about how one of the solutions is microkernel-based I/O services. So I wanted to ask, like, how is managing I/O in the user space any faster than managing it in the kernel? Because I was wondering if the permissions management is any different.
That's a great question, right? So if you simply move your kernel I/O stack to the user space, does that improve performance? Not really. I mean, you avoid one context switch from kernel space to user space, but you also need to do IPC, right? So that itself doesn't really improve performance. So what Snap does is that they have this specialized I/O services, right, within this user space module. And then the application needs to say, oh, I want to use that I/O service. That's a stripped down version of the entire kernel I/O, right? So much simplified and much performance optimized fast I/O path for certain applications, right? But there are other applications, they don't want to use that. They can also use some other I/O services, right? So this in general is called specialization, right? You can do specialization in this user space I/O library to provide faster performance. A really good question. Any other questions? Yes?
So it's specialization. Why can't there be a fast I/O module where you need to strip down some features in the kernel?
Okay, so that's a good point. So first of all, the I/O interface provided by Linux is very rigid, right? So this is mostly an interface problem, right? Because from the perspective of Linux, right? So it just provides this fixed interface called POSIX, and then it cannot change this interface because everyone is relying on this interface, right? If you change the interface, a lot of things can break, right? So I think mostly it's an interface problem, right? So if you use POSIX, then you have to have a lot of these complexities. From Google's perspective, because Google has the luxury that it is used internally by Google, right? So Google can educate its users, and the users for Google Snap is actually Google engineers, right? So they can provide this interface and tell the Google engineers, oh, we have this high performance interface that you can use. It's slightly different from POSIX, so you can get better performance, and a lot of people use that. And then even in the POSIX combined interface they provide, they can change the interface somewhat, right? And then for specialized cases, right? But it is very hard for Linux, which is used by everybody, to change their interface. Yes.
I think I was asking a similar question and but it's more of something like like DKMS. Maybe there could be like a DKMS for this sort of thing.
Sorry, what is DKMS?
Dynamic kernel module or something, whatever.
Okay. I mean, sure. I mean, if you can write kernel modules, right? And you basically modify the kernel, right? So if you are a particular user and then you just want fast network process speed on your machine, you can do a bunch of things to make it faster, right? So you can write kernel modules, you can even modify the kernel source code, recompile, right? But I think it's certainly, so the eBPF I mentioned is one way to customize this kernel behavior without writing a kernel module. Right? For those who know kernel module, or for those who doesn't know kernel module, is a code you write that can run dynamically load into the kernel. But the problem with kernel module is that if you write a bug in your kernel module, you break the entire kernel. So suddenly there's a kernel crash. So eBPF is a nicer way to inject code into the kernel. So eBPF ensures there's some check to make sure that your code is not going to break the kernel. Right? Anyway, so the general idea of like inserting some code into the kernel to make certain path faster, I think that certainly works. Okay, go ahead. So.
The main drawback of separating the control plane and
what's the main drawback?
trade-off compared to the
Okay, what are the trade-offs? So the monolithic way of doing I/O is easier to design because, well, that's the most easy way for you to structure your code, right? So you just write a piece of code that does this. When this packet arrives, you do a bunch of if-else check, right? Make sure that you are doing the right thing. When you do control plane, data plane separation, then it's a completely different way of modeling your I/O, right? So it's a bit hard to structure. And then, so the biggest issue with control plane, data plane separation is that you need to make sure your data plane actually has all the security features you have, right? So I mentioned that with SR-IOV, you can have something like filtering, something like some rate limiters, right? So these are done on the hardware. But if you don't have that, then you cannot have a full data plane with some of these access control stuff, right? But this is not as flexible. I think you lose flexibility. So your data plane, if your data plane hardware doesn't have all this hardware support, then you can't do this, right? But if you do everything monolithically, your code can do anything, right? You can do arbitrary protection policies in your Linux kernel, but you cannot do arbitrary protection policy with the control plane data plane separation, right? Because the hardware is limited. So that's why I think Google went with the microkernel based approach, because with the microkernel based approach, you still have all the flexibilities. You can still write all these policies in code. Okay. How much time do I have? Or should I stop soon? I think there's another talk, right?
I can take like one more.
Okay, one more question. Okay. Go. I don't know. Okay, go ahead. You can come to me after the talk as well. Go ahead.
Do you think microkernel-based approach like OSDI will eventually be preferred for like monolithic? Do you think it's always like going to be the specialized things?
Okay, so that's not. I think that's not a objective question. That's a very subjective question. Whether or not monolithic kernels are better or microkernels are better. So there is no correct answer. Oftentimes, I think it's, for me, I think it's hard for me to imagine that Linux will become microkernel. So Linux is very likely to stay in monolithic kernel for the foreseeable future. But we do see other popular operating systems are moving towards microkernel. So Google is one case. And then there's one more recent case, but I don't know if people are aware, is Huawei has their own operating system. Harmony. So Open Harmony OS is also microkernel, right? So, Huawei's OS it's going to run on billions of devices, right? So you will have a lot of devices with microkernels. And so, I don't know, both have their merits and both have their problems, right? Okay, with that, thanks everyone.